Now we'll take a look at the second component of resource management by operating systems, managing the CPU. We could probably guess from our discussions of memory that that's going to be involved with how we schedule processes to use that single CPU. And even if you have dual-core systems or multi-processor systems, you still have an issue. You generally have more processes than you have CPUs, and you got to make sure that they all share nicely. So let's take a look at what happens to a single process before we put multiple of them in play. A process starts out in a state that we'll call new task. It arrives on the scene and wants to be done. You click on a program and start it up in Windows. First, the operating system has to get the process ready to run. There's some entries in the process control block he's got to set up, and usually he'll also make sure that the first page or two of the process is loaded into memory. Then when the CPU becomes available, you do what's called a dispatch, and basically load the base register, set the program counter to 0, and let the program rip. It'll start running. If it's a short program and doesn't do anything interesting, it'll complete, be taken out of the process control block, and be gone. Most processes, however, want to do some input-output somewhere. Want to get something from the user, want to read something from the internet, or they may just have to wait for the Windows system to let them write something to the screen. In that case, they'll become what's known as blocked. They can't do anything until that event completes or until they manage to get input from the user. When they do get their input, or their event completes, then they can go back on the ready list. They generally don't go back to running immediately. They'll be placed on the ready list, and then, again, when the CPU is available, the operating system will put them back into the running state. Now let's take a look at what happens to two processes and what that all means in terms of the CPU. Well, here's two very simple programs. I'm using PEP8 because we understand how to read that code, where we just load some stuff out of memory, take a look at it, branch around, add some things, store some things, and go ahead. And we'll say we're just going to run two copies of this same program. Two processes, one program. We've got it open in, say, two windows on the system. If the one on the left started first, then as soon as that process is ready, the operating system will put it into its running state. And you can see it'll process 3 instructions and then hit the decimal input instruction, whereupon the user is going to have to do something before it can continue. Noticing that, the operating system will put it into a blocked state. Before he does, however, he's going to have to save what's in the accumulator and save the current program counter. Those will be associated with the process control block. So when we give the guy his computer back, we can use what's in the accumulator and the program counter, because we're about to give that up to the process on the right. For that task, we're going to have to load his base register, clear the accumulator, because he doesn't want stuff in it from the beginning. He's probably assuming it's going to be 0. Set his program counter to 0, and then let him rip. And not surprisingly, he'll execute the same 3 instructions, and then he'll block, waiting for I. We'll save whatever he left in the accumulator, along with his program counter, and now we just have to wait for one of those inputs to complete. Let's say it's the guy on the left. As soon as he completes, the operating system will then load the base register again for process 1, restore his accumulator, restore his program counter, and let him go continue processing. That's a context switch. And now the complication arises, of course, if more than one process is ready, who goes next? Well, let's look at a couple of strategies. Taking a page from the memory management book, let's look at first come, first served. Now, I'm assuming that for whatever reason we have 4 jobs here ready to go, and their run times are as indicated in the table. Well, job 1 was there just before the other guys, so we'll let him have a first crack at the CPU. He runs for 80 milliseconds, and that gives him a delay of 0. We started him immediately as soon as he arrived, and a turnaround till he was done of 80 seconds from when he arrived to be run. Now that he's complete, we'll give the second job a shot. He runs for his 100 milliseconds, but he was delayed 80 at the beginning, so his total turnaround time is the sum of those, or 180. From the time he showed up at the door wanting service, it took him 180 milliseconds until he was satisfied. Job 3 runs for 150, and finally job 4 runs for his 50. Now, of course, these don't necessarily need to be complete at this point. This could have been until they hit their next wait for user I/O or something like that. But just to keep things simple, we'll consider that as 4 jobs that ran to completion, 4 tasks. Now, statistically, what can we say about what happened here? Well, the average runtime was 95. We knew that up front. The average delay for these guys was 148 milliseconds. So on average, a process waits 148 milliseconds under this strategy. And our total turnaround time until they were done was 243 milliseconds. Now, it's a little painful for job 4, who only wanted to run for 50 milliseconds, to have a turnaround time worse than anybody else's. So sometimes we look at that and we sort of weight the turnaround times by how big it was in the first place. We can call that delay percentage, if you will. How much was he delayed from the beginning versus how much did he actually need to run? And you can see that job 4 really kind of got screwed here. He had to wait 330 milliseconds to do his 50 milliseconds worth of work. All right, again, let's try shortest job first and see what happens to our delay, turnaround, and delay percentage measurements. Okay, the shortest job is job 50, so he's going to have the delay of 0 this time. Our next job is job 1. He's now got a delay of 50 and a longer turnaround. Job 2 goes next, followed by job 3. And as you can see at our statistics, all of them seem to have improved somewhat by picking the shortest job first. Now, of course, that's a function of which jobs happen to show up in which order. If they would have all shown up in the shortest job first, taking them first come, first serve would have been exactly the same. Now, the strategy that's actually used in most computer systems today is what's known as preemptive round robin. What that really means is we're going to give each job a little piece of time to get some work accomplished, and then we're going to rip the CPU out of its hands and give somebody else a chance. We're taking turns, if you will, to share nicely, just like in the sandbox with the single toy truck. Well, it doesn't really matter a lot who's going to get started first because it's going to be a short time anyway, so we'll give job 1 10 milliseconds to get going. He hasn't finished anything after 10 milliseconds, so we rip the CPU away out of his running hands and give it to job 2. Job 2 gets his 10 milliseconds, and then it's job 3's. He gets 10 milliseconds, and then it's off to job 4. All right, we can see now the delay has gone way down because everybody's gotten at least a crack at the CPU very quickly. And now we're going to repeat the same process. Okay, these get 4 more slices. Nobody's done yet. And in fact, we're going to keep giving them slices until job 4, who's the shortest job, completes. All right, this sounds pretty good. The shortest guy gets done first, and I'll bet you the longest guy is going to stay in there the longest. Sure enough, 2 more slices, and job 2 is done. Job 1 is done. 3 more slices after that, and job 2 is done. And finally, job 3 gets the whole CPU to himself because everybody else is complete, and he finishes up. Notice that all 3 of these strategies took exactly the same length of time for everybody to get finished. But when we look at what happened to our delay, turnaround, and delay percentages, they're very different. In fact, shortest time first scores pretty well on all of those. Preemptive round robin does really well on the delays, but it actually slows down just about every job, which sort of makes sense. Nobody gets through there in their allotted time unless they're really, really short. So, which of these strategies should we use? Well, again, what are we trying to accomplish? What's fair given our particular environment? First come, first serve, well, it sounds fair, and it's certainly easy to implement. Shortest job first, well, that sounds good unless you happen to be a long job, of course. But the other challenge with this is trying to figure out in advance how long somebody's going to use the CPU. We could ask them to volunteer that information, but would they lie? We could see what they ran the last time, and that might be an indication of what they're going to run the next time. But some guessing is involved to make that strategy. The round robin sounds kind of harsh because we have to rip CPUs away from people's still breathing hands, but it also lets everyone make some progress very quickly. And it has this effect that short jobs tend to finish sooner than longer jobs. But it's complicated, and you can guess it's probably more expensive to implement. So it puts more overhead on everybody. Well, and in reality, the overall situation is better than that, but it's also more complicated. Lots of processes tend to block very frequently. They wait for input, they wait for their output, they wait for page swaps, they wait for something coming over the internet. So a lot of things can cause a process to block and voluntarily give up the CPU. It's not all that common, in fact, that you have to rip it away before the time slice is complete. Think of what happens when you're sliding a mouse around a window. There's a lot of interrupts from the mouse that process wants to hear about. The other problem is, of course, this interacts with our memory management strategy. It doesn't make sense to try and put a short job in for process management purposes if he's going to take up 3/4 of the memory. So you have to actually balance those two, which is why the job gets very artistic in some cases, and there is really no well-understood complete solution for it. We also tend to run things with priority, and this helps a lot. Now, priority doesn't just mean that you're the president, or the principal, or the teacher. It actually has a function of what's going on in your process. Let's think about somebody that we had to rip the CPU away from, and in fact we've had to rip it away from them the last 16 times we gave it to them. Well, they clearly are chewing up the CPU. They are a CPU hog. So they probably are going to get lower priority than somebody who's in and out really quickly, because we know they're going to run forever anyhow. Now, think of somebody who's waiting for the disk or waiting for network I/O or something like that. Well, somebody like that spending a lot of time loading down pictures over the internet. We won't ask what about. We do want to keep the internet happy. We want to keep that traffic flowing back and forth, but we also don't need to give them very much of the CPU because they're just going to turn around and give it right back. Even more, if somebody's mousing around their spreadsheet, we probably want to get back to them quickly. They're going to notice first if something is slowing down. So just to keep the user as happy as possible, we're going to put him in a high priority environment if he's blocking on user types of input or output. And last but not least, we want to think about the interaction with memory management. If we've page faulted somebody, we probably want to put him back at relatively high priority when that page fault resolves and we get his page loaded into memory, because otherwise we're going to risk increasing our thrashing. It would be silly to bring him into memory and then procrastinate long enough before we use that piece of memory that it got swapped out again, for example. So these are some simple examples of how we can use priority to help the process of using the CPU efficiently. All of this means is that our process control block and the management of the process by the operating system is getting very, very complicated. We have to keep track of the whole page table where we know each page in memory is. We have to keep track of saved accumulators, program counters. If you think about it, we got to keep track of base and bound registers. Oh, and remember those status bits? Oh yeah, those need to get restored by the time we get back too. So there's a lot of stuff we got to keep around for each process. We have to manage this complicated set of states. We've got to deal with priorities. It's why it's still an art form. It is complicated, but it's complicated in the real world situations as well. In fact, there's been a lot of cross-fertilization between problems and people that have originally been involved in the computer science area, finding applications in the business world, be it as simple as managing checkout stands to managing complicated inventory supply chains. It's also led to some advances in focus in theoretical mathematics to try and understand these problems at a deeper and more useful level. And you thought it was all just about running Windows.